A certain photoelectric surface has a work function of 2.3 electron volts. If the stopping voltage is 4 volts and the mass of the electron is 9.11 times 10 to the negative 31st kilograms, A. Find the maximum kinetic energy and the maximum speed of ejected electrons. B. What is the wavelength for the incident light? C. What is the cutoff frequency? A. For the maximum kinetic energy. Maximum kinetic energy can be measured using the stopping voltage. When the current stops, that means all that kinetic energy is turned into potential energy, U equals to QV. Therefore, this will be Q, which is the elementary charge E, times V is the stopping voltage. So this would equal to EV, and because we're using electron volts over there, we'll say the charge is 1E, and the voltage is 4 volts. That's the stopping voltage. So the kinetic energy is 1E times 4 volts. That's 4 electron volts. So that's the kinetic energy. And then we want to find the speed. That means I have to use the maximum kinetic energy equals to 1/2 m times V max squared. Now, if I want my speed to be in the standard unit, I will need my maximum kinetic energy to be in standard units instead of electron volts, which is not the standard unit. So I'll have to replace the E with the standard unit in coulombs. 1E is 1.6 times 10 to the negative 19th coulomb. So now, if I do this, I will have the energy in joules. This gives me 6.4 times 10 to the negative 19th joules. So if I make this equal to that, let's see, 1/2, the mass is 9.11 times 10 to the negative 31st times V squared. This equals to 6.4 times 10 to the negative 19th joules. So solve for V, and we'll get the maximum speed to be 1.185 times 10 to the 6 meters per second. And that's the maximum speed. Part B, we need to find the wavelength. First, we can find the frequency for the incident light. We already know the maximum kinetic energy, and we know that maximum kinetic energy is the leftover energy. When an electron catches a photon, it gets this much energy, HF. But then it has to use a certain amount of energy to overcome that work function. So the maximum kinetic energy equals to HF minus the work function. We know everything here except for the frequency. So we can find the frequency using this equation, and then we'll be able to find that wavelength we need. Because we already know the maximum kinetic energy in electron volts and the work function in electron volts. So it can be convenient for us to just keep electron volts. That means when we plug in the H, we will need to use that one with the electron volts times second unit. So the maximum kinetic energy is 4 EVs, and the H has to be the 4.14 times 10 to the negative 15th. The frequency is something we can find first, or we can just say frequency is C over lambda. And then minus the work function 2.3. So this would be 4.14 times 10 to the negative 15th. C is 3 times 10 to the 8th, and then we're looking for the wavelength. So this will give us a wavelength that is 1.97 times 10 to the negative 7th meter. And that's 197 nanometers. And then part C, we want to find the cutoff frequency. The cutoff frequency is the property of the photoelectric surface. It is related to the work function. So let's see, the work function equals to the HF, and this F is the cutoff frequency. So this is the phi 2.3. Again, if I'm using this as in EVs, that means the H we use has to be 4.14 times 10 to the negative 15th. So from here, we'll be able to find that cutoff frequency, which is 5.56 times 10 to the 14th Hertz. Note that this frequency is not the same as this frequency right there. This is the frequency of the actual incident light. But this cutoff frequency is the property of that photoelectric surface, the sample surface. Because this actual incident light produces a current, that means that this actual incident light must have a frequency that is higher than the cutoff frequency.